here, but.
Okay. So, hi, Guilherme. Good morning. Good morning, Stefanella. Good morning, America.
Good morning.
Hello, Adriano. How are you doing?
Adriano, how are you?
Good, good.
Are you better?
Yeah. Right now, I can say 100%.
Oh, good to hear this.
Never say that, my friend.
No.
It's 99.99%.
Yeah. Okay. I'll mute my mic and close my video to improve the streaming, okay?
Como os meninos são bobos? Por quê? A professora, estamos cada uma, a todo mundo ficou falando. Quer dizer, a maioria dos. Não, as meninas ficaram caladas.
Some colleagues are asking to ask you to open the meeting room for them. They are not able to access. Argemiro and Paulo.
Still 1 second. Is that I'm sending the setting up the YouTube. 1 second, what is it?
My students are also saying that they can't access.
I access everyone. Everyone that is in the rooms, yes. One second. Okay. Now we have Jose that is taking care of that while I finish the YouTube. Jose, please let everyone in the room while I'm finishing this. Okay. 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 We're almost ready to go. Okay. Okay, so I think we can. So I have some work nearby here. I have some drilling, but okay. So Nathan, are you ready?
Ready.
Okay, so I'll start the record. There is Bruno living. Okay, so it's It's a really great pleasure to have a colleague, a sort of old friend with us, Nathan Kutz. We know each other since a long time, and he already was the thesis advisor, PhD advisor of 2 students of the ex-students of Applied Math Department, Pedro Maya and Lucas Stollerman. Both now is one in California, one in Texas. So it's a great pleasure to have Nathan. And Nathan, I will ask you at the beginning to give a brief summary or your trajectory for the student to understand the kind of skill, how to acquire the skill to work in such in interdisciplinary environment. So it's always good for them to get ideas. So please, Nathan, thank you very much.
Okay. Well, good morning, everyone. It's nice and early here in Seattle, where I'm stationed. I hope everyone is doing well, despite things like COVID happening in the world. Yeah, so math keeps going. So we keep doing our thing, and despite COVID, you can work around and keep doing your interesting science and math, and hopefully that has been something interesting for you to do during these times. So yeah, I am here at the University of Washington. I am a professor. I've been here now more than 2 decades. And so I got here really by I did my undergraduate degree here in Seattle at the University of Washington, and I did it in physics and math. And then I went to Northwestern to do a PhD in applied math. And one of the things I always loved about applied math was how much diversity of the kind of problems that people consider, right? You can do anything from mathematical biology to computer science problems to physics problems. And it was all okay to do that in applied math. And I really enjoyed that aspect of being in applied math. I went on to do a postdoc with Phil Holmes at Princeton after my PhD, where I did a lot with dynamical systems. And so I always think about almost everything as a dynamical system. I think about when we think about measuring things that are changing in time, these are all classes of dynamical systems. And I spent a lot of time trying to think about how would we model these things. And I've been very fortunate to be able to do this across a really large variety of problems, from nonlinear optics and laser work to neuroscience. All these are dynamical systems. And so you can use a lot of these tools together to do some interesting things with them. And in fact, that's really what I want to talk about today, is thinking about dynamics and dynamical systems from the point of view now of data. We have a lot of emerging methods around data science that are coming to the table. And one of the questions you have to ask is, what can I do with data? How can I use data to build models? What we've tended to do is for us to build models and then see if it worked with the data back. And we've always used data, but now we have a lot more of it, and we can collect data very quickly. We can fill up whole hard drives in minutes just with collection of our data and having better sensors. And it's opening a lot of new possibilities, especially in biology, where I think that we're being able to collect data and we don't have good first principle models, right? There's not a F equals ma or Maxwell's equations in biology that are so readily available to us. And so we need to start building models directly from the kind of interesting data we collect. So, this is I guess this mini tutorial start today, and they go through next Tuesday, right? And so within this block of time, I want to cover a number of topics that I think are relevant for you to think about when it comes to building models. And I've broken it down roughly into 3 pieces. One is to think about, how do I discover from data governing equations? In other words, I measure a system over time. Can I discover some kind of evolution equations that describe that? So I don't have to prescribe them ahead of time. I discover them from the data itself. Second is this idea of learning coordinate systems And that's actually just as critical as discovering and governing equations. And I'll talk through this a little bit so that you kind of understand where my perspective comes from. And finally is the fact that we actually have to deal with real measurements and sensors, right? As much as we would like to have access to great data, we can often do it synthetic with our simulations. When you actually measure a system, you're pretty limited by either your sensors or the actual physical system you're trying to measure. Biology is a great one. Like if you're trying to get data from neuroscience, you can't record all neurons at once, right? We are getting closer to doing whole brain imaging, but that's for simple creatures. But normally you record a certain subset of neurons, and then you would try to build models from those. Okay, so the theme throughout this whole thing is going to be centered around two key concepts. One concept is going to be the concept of discovering governing equations. The second concept is going to be around discovering coordinate systems. So that's the two things I want to really highlight that are going to be important in this set of lectures. Okay, let's talk about coordinates and dynamics. So those are the things we're going to pair together. Now, the first thing I present here and show you is going to be in some sense where we're going to go. And the idea here is, and I've drawn this in a neural network architecture, but it doesn't have to be a neural network. What we're looking for is when I take the data, and that's over here, this input data level. So that layer that comes in, this is your raw data. And just because you measured something doesn't make it the right variable to work with. So part of what you would like to do is move yourself into a coordinate system in which you can more effectively prescribe the dynamics. And then that phi there is an inverse back to your original measurement space. And part of where I'm going to go with this, and this is going to be lecture 3, which is going to be next week, will be on, one of the great things about neural nets is that they are amazing for doing this discovery of good coordinate systems, even if you don't know what the right coordinate system is. But let's talk about what we have done around this framework historically. So first of all, in discovering coordinates, through a lot of the 20th century, in the 1900s, we were doing a lot of physics using these special functions, Bessel functions, Hermite, Laguerre. What they were functions that were ideal for a certain geometry of a physics system. And so it made a lot of sense to use those coordinate systems to model your dynamics, right? So for instance, if you had a vibrating drum head, Bessel functions were ideally constructed to model that system, right? Cylindrical coordinates. And this is exactly what we did for most of the 1900s, is we had a lot of expert knowledge, we knew a lot of these special functions, and so we used them extensively throughout physics. Now, since that time, and since we've been starting to use more data-driven methods. In particular here, I put what's called SVD-based, singular value decomposition-based methods. And so what these are methods in which you can take data and you look for the dominant correlated structures or subspaces on which the data lives. So these are often called principal component analysis. That's equivalent to SVD. But it actually has lots of names. This is what's fascinating about SVD. You know it's a great method when many fields have independently developed it and essentially used it, but they don't even know that these other fields have the same thing with different name. So for instance, in fluid dynamics, it's called POD, which is proper orthogonal decomposition. In atmospheric sciences, it's called EOF, empirical orthogonal functions. It was also called a Hotelling transformation. So all these things are equivalent to each other. They're a singular value decomposition based technique which extracts dominant correlated structures and allows you to build a coordinate system around them. And then finally, what we'll get into later is the emerging concepts from neural nets. So this is another way to get at a coordinate system, is to use neural network transformations. So instead of the SVD, which is a linear transformation, what neural nets allow you to do is these very complex nonlinear transformations. And so we want to exploit that when it's appropriate. Okay, what about the dynamics itself? So you have a coordinate system. So what? So now you're in this coordinate system, and what do? Well, now when you're in this coordinate system, at least for these dynamic problems, in this coordinate system, you see how does the system evolve in time, right? So you have time series data in this coordinate system. And so what you'd really like to ask is, all right, so what am I going to do to model the time dynamics? Well, we've done a lot of different things to model time dynamics. One of the methods that comes right out of statistics literature is called autoregressive moving average models. These are ARIMA models, right? So this is a statistical technique for modeling time series data. There's also things like dynamic mode decomposition and Koopman models, and we're going to talk about those as we develop out this lectures. So DMD and Koopman are things we're going to talk about directly here, and what they are is, once I'm in this coordinate system, can I construct the best fit linear dynamics model describing those the time series evolution. We also have other methods like SINDy, which stands for Sparse Identification of Nonlinear Dynamics. And this is a model discovery technique, which is, once I have the time series in this new coordinate system, can I discover governing differential equations or partial differential equations which prescribe how this thing is evolving in time? You can also, when we think about time dynamics, if you come from a dynamical systems perspective, you can do things like normal forms. And there's also things like more modern techniques of neural nets using what are called LSTM GRUs. This stands for long short-term memory modules, echo state networks, recurrent networks. These are all things that help model time series behavior. So you have a coordinate, and then you have time series. And so these are the things we want to go after in this. Now, if this seems a little too high level, what I want to do is bring it back and tell you why I am so motivated by this picture in what I do and what I think a lot of people are doing in the community. So let's talk about good coordinates first. And let's talk about this in the context of one of our most, longest term, most important science problems we've maybe ever had. And that is celestial mechanics. So for thousands of years, right, we as a human species studied the stars, and we were very interested in what was going on with these planets. So here, for instance, is the retrograde motion of Saturn and Mars. So Saturn is in the left there, and Mars is in the front. It's got a little bit of a reddish hue to it. And so this is a picture of the night sky and watching how this planet is evolving from the Earth frame. So one of the big questions was, for the ancients, in fact, for a long time, people were trying to say, can I predict the motion of the planets? Can I make a forecast of where the planets are going to be, a year from now, 10 years from now, 100 years from now? And how accurate are my predictions? And so this was a study of great concern. And so we started really thinking about this. And in fact, one of the earliest theories of this that was successful was the Ptolemaic doctrine of the perfect circle. So the idea was that from the Earth, one way to describe this is a circle on circles. So in fact, you have these beautiful paintings. Here's an Italian painting of this idea of the doctrine of the perfect circle, which is essentially, one way to think about it is the motion of a planet is a circle, and it's on a circle, which is on another circle. One way to think about that is that was the first and earliest Fourier transform, right? Move this thing onto a coordinate system, which is a bunch of frequencies. And by having those frequencies and their radiuses, you could describe the motion of Mars, Saturn, Jupiter. All those were described. That was the most accurate description of the paths and the trajectories of these planets. So the other thing about this was the Ptolemaic doctrine of the perfect circle came around the 2nd century AD from Alexandria, Egypt, right before, right around the time when Rome was starting to take over the entire world. The Ptolemaic dynasty had a rich culture. They had the Library of Alexandria. They had the leading intellectual thinkers of the day, and this is their theory, and it was quite accurate. In fact, it may go down in history as the longest, most successful theory we've ever constructed, because it lasted for 1,500 years, roughly, before it was taken down. I think it's very hard for a theory to last that long. And that one is just amazing that it was that successful for that long. So is it right? Well, it did a great job. And being right is all a matter of perspective. What we learned afterwards is that, well, actually, that's not quite how we should maybe model this. And along came some people who really challenged this. What I've shown you here is a picture on the bottom left is Kepler and Galileo. Really were building on Copernicus's idea that maybe all these planets are going around the sun, that in fact, it's not an Earth-centric rotation system, it's a heliocentric rotation system. And in fact, that's why you see the retrograde motion. Viewed from the perspective of a heliocentric universe, the retrograde motion made perfect sense that Mars and the Earth are both in some kind of orbits around the sun. They still, thought it was circular until Kepler really showed with Tycho Brahe's data. It's actually, we are on ellipses. And that makes a huge difference to move to the elliptical orbits. And so that was the first foundational step, which really led to what came about in the scientific revolution, which is Newton proposing F equals ma. By the way, we do not get Newton's laws, F equals ma, until we have the right coordinate system. So this is really important. It wasn't just about F equals ma. It was also about having this in the right coordinate system. Heliocentric universe, then F equals ma. You need the two together. Now, the reason I put Einstein here is we know from the early 20th century that Newton wasn't right. He was mostly right. We still use F equals ma quite a bit. But really what we're finding out is we have this curved structure to space-time. So general relativity came about, which was an improvement of the model that we had and you know that we're still going to figure out somebody is going to be a picture on the right of Einstein there. Because what we're going to figure out is that, oh, Einstein wasn't quite right. As we get better measurements and better data, we're going to figure out how to make better theories. And in fact, the reason general relativity came about is because F equals ma model, we were able to measure so carefully that we found there was a discrepancy between the Newtonian mechanics and what was actually observed in some of our planetary motions. And general relativity accounted for that discrepancy. That idea of discrepancy is going to play a role for us a little bit later. Okay. So we get to a really important point here. So far, this is kind of almost philosophical discussions a little bit about this, but I think they're very important. And it gets us to this piece here, which is, I want to put Kepler versus Newton. So let's talk about these two people. Specifically, start with Kepler. Kepler wrote down his laws. He was able to construct elliptical orbits, really that map out the trajectories of the planets. And what's interesting is set the foundation for calculus and F equals ma. That comes about 100 years later. Now, when Newton gets his F equals ma, what are the solutions for those planetary motions? Well, They're just the ones that Kepler had. So here's the question. Why do we always think that Newton was the greater scientist? I mean, you can look on Google and look online and see best physicists ever, and Newton's always at the top. Kepler's, you know, I think he makes top 20. And the reason, because in some ways, to say it, Newton just got the same equations, same solutions that Kepler did. So why is he more famous? And here's the important difference. Once you have F equals ma, you can do something you could not do that what Kepler did. You can say, what would it take to launch a rocket from Earth and land it on the moon? What Kepler did was fit data to a model. He interpolated. In other words, he took the data, he fit a model to existing data. His model did not extrapolate. Kepler can extrapolate. Newton can extrapolate. Once you have F equals ma, it is the ultimate interpretable and extrapolatory model. You can imagine things and start planning trajectories you've never seen in your data. And this is in fact how we launch missions out to the planets and to the solar system, is because we're just using governing equations to be able to do this. This is something Kepler could have never done. Now, the reason I highlight this difference between them is because their legacies are very much in data science today. And let me give you the example. On the top, you see a robot from Boston Dynamics. So this just came out in the spring. They released this new video, and this robot is much more athletic than me. And it's amazing. Look at that. It can do great things. On the bottom is a self-driving car. And it is similarly amazing. It's basically can do pretty sophisticated driving on very crummy roads, through traffic, construction zones, all of these things, right? So our self-driving car technology is really coming along. And there is a, however, they're both autonomous vehicles, right? So one of them is the robot. You can think of the car as a robot that you sit inside if you want to think about it that way. But what's the big difference? The robot is completely built with physics models. It is imbued with F equals ma. As much physics as you know, you put into this system. So it's kind of a Newton approach, which is I bring all my physics into this to build a better robot. And one of the reasons you need that is because the robot is inherently unstable, right? Just making a robot walk without falling over is actually a pretty remarkable task. You need a lot of control to make this happen. So you need to use all your physics to control it. The self-driving car, on the other hand, if you walk away from your car, the car doesn't fall over, right? The car itself is like inherently stable. And in fact, the self-driving cars make use of no physics. It's all sensor banks. It's like Kepler. You take the data, you fit a model. And so this is a big difference. Both are very successful, by the way, right? We're having success building robots. We're having success making self-driving cars. But they're taking very different directions when it comes to data science. One which tries to build interpretable physics models, and another that just says, I don't need them. If I have enough data, I can use just my sensors and it can learn from the data how to self-drive. And so these are going to be things that you should start thinking about of how do you want to go about your modeling with data. And in any case, these are really getting after this idea of coordinates and dynamics. Those are the two key concepts in all of this. So I do want to, this is it here. So physics and no physics. So, you know, obviously you probably have an opinion about the kind of things you like. I tend to go towards the top. I like to build models that I kind of understand more what they're doing. However, I do recognize there is sometimes great value from just taking data where it's very hard to get any kind of interpretability, and you can just make something work in pieces. In fact, one of the things we're going to do, I'm going to really highlight, is this idea of really using targeted use of neural networks to help you do things that are interesting and interpretable.
Nathan, may I ask a question?
Yes, yes.
Suppose you're in a situation that you have enough data and enough knowledge of the physics that you can use both approaches. Doesn't matter, you're able to use both. Which one do you prefer?
Well, actually, I think what people are really doing now is if they can use both, they use both. So let me say it this way. If you're working at Google, oftentimes the self-driving car people, they're using no physics. They just say, just give me more data. The robotics people have realized that their physics models aren't good enough. And so they need to use the data and use data simulation. I think the future for us is to be somewhere in the middle here. So you're using as much physics as you can and as much data as you can.
Mm-hmm.
Okay, so with that said, let me just skip forward to this here. Here's what I want to get to. So let's go about trying to figure out what can we do then with data and with modeling, because we actually do have a lot of physics knowledge that we learn from our classes, and we want to use those, but we also would like to maximally exploit our data. So the first question I always tell people they should ask when you have data is, what kind of data do you have? I mean, let's get realistic about, you can't determine what you want to do with data until you ask this question here, which is, how much data do you have? That was supposed to be quality. Quantity is the second one. So how good is your data? In other words, how noise free is it? How much of it do you have? What are you actually measuring? In other words, this idea of observability is you have sensors pulling in data, but is that really representing the state space, or how much of the state space for the model is it really representing? And then the most important question is the model you're trying to build fundamentally extrapolation or interpolation? The success of machine learning in the modern era has all been in interpolatory problems. This is speech, computer vision, self-driving cars. They've turned these problems into interpolation problems. That's where neural networks work great. For a lot of what we need to do in science is extrapolation, and it doesn't work well there at all. Extrapolation is very difficult. The only thing that really works well in extrapolation, in my view, is some kind of parsimonious representation of governing equations. I want to come back to that. But this is a big important question to ask before you start. And then let's start getting into the mathematical foundations now. So here it is. This is the mathematical framework I want to think about throughout this set of lectures. First of all, I have a dynamical system. There it is, dx dt equals f. Okay, so f is the function that prescribes the dynamics. It has some parameters, theta, and it may even have some stochastic effects. But there's some governing equations, and this is what you're going to measure. But of course, it's not always clear you can measure x. So you actually have a measurement y, which is some function of x. So this measurement model h. So you're going to measure this, and it has noise. So you measure, you have a measurement model h, and so you're not directly measuring x. You're measuring some function of x, y. And in fact, it's at discrete time points, t of k. So here's the question. I'm going to give you a bunch of measurements, y of t of k. I want you to tell me what the measurement model is. I want you to tell me what the dynamics were. I want you to tell me what the parameters were. I want you to tell me all of it. just from the measurements. And this is an ill-posed problem. It's impossible to do because you have your data and there's an infinite number of ways I could make some kind of model and measurement space. And so what you really need to do to solve an ill-posed problem is to provide constraints or regularizations. In other words, take a system like this and say, okay, fine, it's ill-posed, but I will put additional constraints on the solution types I want. And that's what we're going to talk about, how we're going to do that here. And the constraints that we're going to put on it have to do with interpretability and parsimony. This is where the first set of lectures are going to go. And this is an old idea. It goes all the way back to William of Ockham, where he proposed this idea of a nominal representation of the dynamics. You should make a model that's sufficiently descriptive, but not overly descriptive. So if you just adding variables to describe something is a bad idea. That would be something that Ockham and also Pareto would suggest is not what you want to do. They have this concept of nominal models. In other words, a parsimonious representation of an explanatory model. So in my view, the ultimate physics regularization, so the regularization is just constraint, is this idea of parsimony. So what I want is to limit the number of terms and dimensions to make these as small as possible to explain the dynamics and yet not make him any harder, okay? So this is going to be the regularization that we're going to use throughout this, and really try to build interpretable models, interpretable machine learning. Okay, so let's start with the first theme of this. Let's go after this problem using this idea of model discovery. So what I want to do is I want to take data from a system, and I want to discover I have dx dt equals f. And what is f? If you just gave me measurements of x, could you find f? And for right now, we'll assume that my measurement is x. So in other words, the h, the measurement model, is the identity. So my measurement is the state space. We'll just do that. So to do this, here's your sophisticated mathematical technique you have to know. Ax equal to b. So, you know, look, I teach in the math department here, and a lot of people come in and discount Ax equal to b. It's like, oh, well, is there anything really interesting in Ax equal to b? I mean, isn't that so old that we just don't really think about it anymore? And what I would suggest is actually thinking about this has changed my life because it turns out it's amazing. And in particular, I want to think about Ax equal to b. When we teach linear algebra, we often teach, oh, you know, an n by n matrix. Well, in data science, there are no n by n matrices. What you have are matrices that are massively overdetermined or massively underdetermined. Okay, so this is kind of an interesting thing. So data science today, that's exactly where you have to start operating, is understanding that you could have a scenario where you have lots and lots and lots of constraints and measurements with few variables. And so you have an overdetermined system. An overdetermined system means you can't solve it. You don't have a solution that satisfies Ax equal to b. The underdetermined system, which has very few constraints and lots of variables there, means there's an infinite number of solutions. And yet, if you have MATLAB or Python, you can just do some like hit the backslash and you get a solution. How is it possible it got a solution for you? You had either infinity or zero, and yet out comes a solution, no problem. So what was it doing? In fact, let me show you here on the right. I don't know if any of you guys use MATLAB, maybe you do. But on the bottom right are 6 different ways to solve Ax equal to b that are just built into MATLAB very easily. And that tells you a great deal. It tells you that in fact, this Ax equal to b problem, and specifically over and under determined systems, there are a lot of ways to enforce regularization. It's an ill-posed problem. So the way you get a solution is you have to impose a constraint. So one way to think about this is the way I wrote it was wrong. If I'm over or under determined, I say, I want to solve Ax equal to b subject to some regularization. So I pick something to put there. Okay. And by the way, more generically, this is the exact framework for neural nets. You're solving some kind of nonlinear system of equations now, subject to some regularization. And typically this is a compositional structure, and that's just a neural net, but it's really the same concept. Solve these given some constraints. Okay, so that's going to be important for us to start thinking about. So let's go about it, and I'm going to tell you exactly the constraint I want to impose, which is going to go towards this idea of parsimony. So suppose I have a dynamical system, dx equals n. I put n in there because it's nonlinear. And the question is, what could n be? Well, I'm in my office, right? And I don't know if you can see me in my little square over there, but over here I have a bunch of learned books, right, with lots of math things in them and lots of governing equations. And so I actually have a lot of experience of what n might look like. I have Maxwell's equations, I have Schrodinger equation, I have Lorentz oscillators, I have Kerr-Motor oscillators. I have all kinds of examples of what a right-hand side looks like. And so what I can do is I can make a library of all these different right-hand sides I've seen from models I've played around with. So what I do is I make a library of potential right-hand side terms. And here it is. So theta is, what theta x is basically my library. So every column of theta is a potential right-hand side term. So for instance, it could be a constant. That's what the 1 is. It could be x, which means linear terms. xp2 means, polynomials of degree 2. So quadratic terms, cubic terms. You can have sines, cosines. It's only limited really by your imagination, what you could put in there. The point is, every one of these is a potential candidate to be in that right-hand side. And every row of it is a different time measurement. So I start T1, T2, T3, all the way to some T of M. So I have a lot of time measurements. In other words, a time series of this, and I can evaluate all these library terms. So let me give you show you how this might work. And this is going to frame our AX equal to B. So that library is my matrix A. And here's how I'm going to construct it. Let me just walk you through an example. This is the Lorentz system. So what I have over there is the Lorentz oscillator and, the Lorentz dynamical system. And what you have there, it's some nonlinear system. It's a 3x3, but all you give me is the time series for X, Y, and Z. So that's all I have. I don't know what produced it. So what I do is say, well, if I have X, Y, and Z, I know my model is X dot equals f of X. So if I have those state spaces, I need to compute the derivative X dot. So you can do that. Typically, you want to use a more sophisticated differentiation routine than finite differences because you get better derivative estimates. But if you compute those derivatives, that's the vector B in AX equal to B. So what I'm showing you there in the columns of the X dot, Y dot, Z dot is you can compute that. That's the B. The matrix A is your candidate functions. And there, what I show you there, the theta of X or the candidate functions are all polynomials to degree 5. I just made that up. Say, OK, let's consider candidate functions polynomials to degree 5. And then you solve AX equal to B. And that's what the XI are. The XI are the solutions to that AX equal to B problem. Now, this problem is overdetermined. So if I just hit backslash, it's actually going to do a least square regression, which means least squares tries to make all the solution values small as possible. So what you would get is it would tell you that the loadings, or in other words, the coefficient in front of all those library terms would all be very small. And it would tell you that everybody in the library contributes. But what do we know from physics? What we know from physics is we often think about dominant balance physics, which means there should not be very many terms on. There should be just a few terms that matter. So what I should do is solve AX equal to B, and I want a solution that's sparse. So what we do is promote sparsity. And there's different ways to do this, but typically you promote sparsity by the L0 or L1 norm. I want the solution with the smallest L1 norm or L0 norm. And that's going to promote sparsity in this thing. Now, if you do that, what you end up getting if you promote sparsity, you solve AX equal to B, promote sparsity, you see where those dots are? Those are the non-zero elements when you solve this system. And those terms, if you look, actually, they're exactly the Lorentz oscillator. So what you've done is from the time series itself, just solved AX equal to B by promoting sparsity. And what you get back is the governing system of equations. So you get back the Lorentz oscillator. So this is a really nice technique because, first of all, the math is simple. It's AX equal to B. So hopefully everybody's happy about that, right? It's not like I did some really crazy sophisticated math. I told you that this is just AX equal to B for an overdetermined system. And to regularize it or to constrain the solutions, I said, give me a solution that is the sparsest possible, which you can do with promoting the L1 norm, for instance. You can add noise to this, and you can still get this thing to identify the system. Noise is a big issue. We worked very hard on trying to make it so it can handle more noise. And if you do have quite a bit of noise, you need to make sure to be using something like better differentiation routines like total variational derivatives and so forth. Here's a harder problem. Let's identify fluid dynamics, the flow around a cylinder, which is what we can do is take flow around the cylinder. We can look at the full vortex shedding that goes on behind there. And then what you can do is you can do a dimensionality reduction, which you can take snapshots of this, look in a low dimensional space with the SVD. And what you find is when you look at this low dimensional space is that there's three modes that matter. And there they are, in the modes in the middle. And once you look at the time series in these modes, you do this SINDy regression. And what you find is a dynamical system describing this. And in fact, what's interesting about this is we get the same governing equations as was derived by Bernd Nowak and others in 2003, which describes the Hopf bifurcation that happens in this flow around the cylinder problem. So that equation, it took 30 years to come up with it. It was proposed in the 70s early on that, in fact, there's this Hopf bifurcation, and it was a route to chaos for turbulence. And people were interested in, well, how do we get this Hopf bifurcation out? Well, finally, with some very careful asymptotics, 2003, Nowak got this. We just took the data and got it immediately, right? We didn't have to work that hard. We let the data tell us what the model was versus us going back to the Navier-Stokes, doing all these asymptotics, multi-scale pole parts. We just said, oh, here's the data. Oh, here's the model. So it's kind of nice. Clean data. And we can do things like that. We can also turn this around. And I've included some things here that are particularly interesting potentially for biologists and chemists, which is this is work with Neil Mangan, who was a postdoc with me a couple years back. And what we were trying to do is say, well, what happens if your governing equations take that form there, where you have a numerator and a denominator? So the SINDy architecture is hard because if you write that out, it's not it's a Taylor expansion that goes on for infinity, and so your model really is two short bursts. It's an implicit form, and it turns out that you have to modify this regression framework to handle it. But we did that by taking the FD over to the other side. So you have FD x dot. And of course, one solution to that is just set all the loadings, all the coefficients of your libraries to 0. And then you get 0 is equal to 0. So it's satisfied. And that's exactly what an optimization will tell you. But here, what we do is say, well, once we move it to the other side, we can move the f of n to the other side. And then we look at the sparsest vectors that span the null space. And so it's a modification of this basic architecture. But what it allows you to do is handle problems like this. This is this Michaelis-Menten model. And what it does for you is allows you to handle, you can see there what the kind of model it looks like. And so it's allowing you to discover these equations that come out of chemistry and biology and chemistry, and which we couldn't handle in the original version of this sparse regression. But now you can handle this by doing it in this framework. And it's the same thing, sparse regression, AX equal to B. Okay, so I just want to emphasize that this is what I love about this mathematical technique is it's really pretty simple. Okay. This gets us to an interesting point, which is I'd like to connect this concept to what people often do in terms of model selection, right? So oftentimes when we think about models, we think about potentially computing AIC metrics, BIC metrics to evaluate the goodness of fit of a model. And so there's this very nice concept that happens here that's really in line with information criteria for evaluating models, which is commonly done in biology. So what I'm drawing on this picture is on the y-axis is the error. On the x-axis is the number of terms in a model. And so one of the things that you see right away from information criteria is that information criteria penalizes the number of model terms you use. It very much says, look, if you have to use more terms, it's going to penalize it because there's a 2k minus 2 the log of the log, 2 of the log of the log likelihood there. Okay, so it really promotes using smaller number of terms. And so there's this idea of the Pareto front that comes in here, right? Which is this region where if I don't use enough terms at all, if I don't use any terms in my model, then in other words, my model is dx dt equals 0. In other words, just some constant. Then I probably have a very large error in my model. As I add terms and add richness to the model, my error might go down. But if I just keep adding terms, my error could keep going down. But what I do is I stop once I have enough terms where my error has dropped, and adding additional terms, only marginally improving it. Okay? So this is this idea of parsimony played out, which says only use as many terms as you need, no more. And that's exactly what this sparse regression does. Try to set all these terms to 0, as many as you can, and still get a good model. And so in fact, we actually, yes, go ahead.
Can I ask a question in this context? Imagine you have SINDy, but you try to promote the sparsity. You have a plenty of possibilities how to introduce a sparse structure in the regression. Suppose you use 2 different techniques, suppose lasso and sequential threshold least squares, and each one give you a different solution, but both have the same number of parameters. Which one you should choose?
Oh, yeah, okay. So let me make a couple comments about the lasso. So when we do sparse regression, thank you. So some of you guys are aware of lasso, which is basically AX equal to B, same thing, and promotes a sparse solution. One of the problems with lasso is it's known to make a lot of mistakes on its path, an elimination pathway. And in fact, Emmanuel Kendez wrote a paper, came out in 2017 on the archive. I think it got published in 2018 or 19. And basically he does a very careful study, and he shows that lasso makes a lot of mistakes on the elimination path. So I would never recommend lasso. And this is why people started using things like elastic net. Like if you use a little bit of lasso plus a little bit of L2 regularization, it helps stabilize the lasso. What we do is the sequential least square thresholding. And more recently, we've developed this technique called sparse relaxed regularized regression, which seems to do the sparse solutions much more stably than these other methods. So I would try to pick the most stable of your sparsity promoting techniques. That's the best way to go.
Mm-hmm.
Thank you for the question. Okay. But getting back to here with the model selection information criteria, you can use this same idea here in this SINDy modeling framework. And again, I just wanted to highlight that, this model selection idea of using minimal terms, it's old, right? So if you wanted to evaluate a set of models, you go back to the 1950s where we were starting, Kolbach and Liebler were talking about this KL divergence scores, right? And so in the 1950s, there was already attempts to say, all right, how do we judge between models? What are the criteria? So KL divergence was the criteria that was sort of that won out and was adopted. And then in the early 70s and in the late 70s, Akaike and then Schwartz came up with AIC, BIC metrics, and which sort of is still commonly used today. They are sort of the tools we use today, and they're great. Typically, however, every model you would evaluate, you'd have to do lots of simulations for. So you're really limited when you do BIC, AIC to a limited number of models. You can't do combinatorially large set of models with this because they'll destroy you. So the nice thing about this SINDy architecture and this regression framework is what it allows you to do from a model selection perspective is it allows you to downsample massively to models that live near that Pareto optimal solution. And then you run BIC, AIC on only those models instead of all combinatorial models. Because what SINDy will give you is a combinatorial large set of model spaces. But you can use it in combination with AIC, BIC to say, well, actually, SINDy will actually give me a bunch of models that I can evaluate that are on that Pareto frontier in the Pareto optimal region. And then I will do AIC and BIC on those and then select from there. And then I can determine which models have strong support, weak support, or no support. And in fact, we've been able to do this, and it gives you some pretty nice results this way. And then again, it connects you back to some of this classic literature about evaluating models, which is really important if you're sort of doing biological systems, I think. So you're not just limited to standard like, dynamical systems that are ODEs. You can also discover partial differential equations, so spatial temporal systems with this technology. So here's some way to think about it. And we actually did this, right? So we take fluid data. So here's some data that's involving fluid dynamics. And now when you build your library, it's going to be a much bigger AX equal to B, because now what you have, the state space is the full regime of the PDE, so your spatial region, okay? And then your library now includes terms which have spatial derivatives. So your library is bigger because now you have derivatives, nonlinear derivatives, derivatives of nonlinear functions, plus all the ones that you had before. But it's the same thing, it's AX equal to B. And so you can build a library. And what you find from this is by sampling that fluid flow, directly from the sampling of the fluid flow, you can build Navier-Stokes. It discovers the Navier-Stokes equations for you, which is, I think pretty remarkable, right? More than that, what Sam Rudy did, and by the way, Sam graduated a couple years ago. He's now postdocing at MIT. So if anybody heads up there, he's over in the actually mechanical and aerospace department, doing some work on data-driven modeling. But he showed that also you could say, well, actually, since PDEs hold in local patches, right? So a PDE holds even in a local area as well as global. You can just take a bunch of local patches, so you can massively downsample this PDE and still discover Navier-Stokes. And he was able to show you could do this for all kinds of systems, and including you could do things like also do Lagrangian measurements. What if my sensor was attached to the flow field itself? So here's a random walker. So you, instead of having a sensor that stays in place, this sensor moves with the dynamics. And if you do a histogram of this random walker and the sensor on the random walker, then you can do a regression and find that, oh, you can discover the heat equation. Now, this is a classic result, right? But it's nice to be able to do it just directly from a data-driven perspective. We didn't use any other knowledge except for like, what could it be? What are the candidates? There's a bunch of candidates. You regress, you find exactly the one that you know is actually true from theory. You can also do disambiguation. So if you see two waves a wave passing by you, there's actually quite a few different PDE models that could produce a wave that travels by you. So which one would you use? Well, once you see a couple different trajectories, so for instance, instead of seeing one wave, I see two, you can disambiguate what would be, let's say, the one-way traveling wave equation to something like the KdV. This disambiguation is really important. You need multiple trajectories of a system in order for you to say what's going on. And probably what I'm going to do is going to finish on this slide here and just kind of highlight some of the things that Sam was able to do. It's like what you're seeing there on the left is a bunch of different spatial temporal systems that are sort of, they show up in a lot of different places in mathematical physics. And so what we said is like, I just give you that data. And could you discover the governing PDE? And we can. Some of them are more limited in the noise they can handle, but these are fairly complex. Even something like Komodo-Shivashinsky, we can discover that even though it's got chaotic dynamics. So one of the things I want to highlight here is, so for those of you, like, you know, especially if you're doing biology and spatial temporal biological systems, this is maybe is a really powerful framework to think about. Like, I don't know what my coarse grain evolution dynamics are. I can use the data to maybe directly discover some model that's actually what the data is telling me versus me trying to write down a model and see if it looks right. Okay, so all of this, AX equal to B, you simply say, here's a bunch of potential candidate functions, and you just solve AX equal to B with promoting sparsity, and what you discover on the back end of this are governing equations. And this is a good place to stop. So let's take questions and take a little 5-minute break.
Great. Thank you very much. Really great lecture. So are there any more questions? Adriano, Amerigo, or maybe at the end?
Yeah, I have a question for Dr. Kutz.
Yeah.
Yeah, it's a very nice presentation you gave here. It's impressive. And about this SINDy approach, you know, when you transform the problem, solve the AX equal to B, and also the implicit SINDy when you have some nonlinearities in the parameters that you can decompose that in the numerator and the numerator function and do the implicit in the SINDy. That's fine. But what about when you have another kind of nonlinearities in the parameters, some kind of exponential function and the parameter on that exponential? How you deal with that with this SINDy approach?
Yeah, so we just recently actually did that, or at least made an attempt. So your question really is, suppose my right-hand side, there's a e to the alpha t, right? And even in my library, I might say I could put it e to the t, e to the 2t, e to the 3t. How do I know to prescribe not only an exponential, but the alpha? And so in what we did, a paper just actually, I think it just came out, we actually used this sparse relaxed regularized regression technique to simultaneously do two things. I can put in there a library term like e to the alpha t cosine omega t, and during the regression, it will decide, is this exponential in here? And if it is, what is the parameter alpha? Is this cosine in here? And if it is, what's the omega need to be? So it determines the parameter as well as the inclusion of the function, both. But that's very new. But the way I presented it here, you can't do it. It has to either be in your library or you're done. And that's one of the questions you can always ask is, okay, but so now I have to make sure I have a really great library for this. And some terms, so in fact, if you look at these governing equations, one of the reasons we can get away with this in the architecture, in my view, is that a lot of the physics we ever see is dominant balanced physics. There's just a few terms that really are dictating the dynamics, even though there's a lot of small stuff floating around, a lot of other terms, but they're very small and negligible. But this architecture of being able to put in more interesting library terms with parameters, that just has recently been done by setting up a new optimization routine.
Okay, thanks.
Mm-hmm.
May I ask another question in this context and made a comment? Nathan, this question Argemiro asked, in the beginning of this year, we tried to use SINDy to recover the dynamics of a pendulum. So you have a sinusoidal nonlinearity in the evolution law. But we try to test the capability of it to reconstruct the evolution law only using polynomials without including a trigonometric function. And it worked relatively well, captured the Taylor series approximation for the sinusoidal term, but it captured some spurious terms, some spurial polynomial terms that has nothing to do with the physics.
Yeah, so
in the beginning, we thought it was a issue related with the energy dissipation of the integrator you use it to generate the series, because the spurious term was a dissipation term. But then we tried with energy conserving integrators, and the problem persisted. And we are able to solve this changing the basis. Instead of using the classical monomial polynomial basis, we changed it to a Legendre basis and recovered perfectly the evolution law. Could you comment this?
Yeah, well, and here's my only, I don't know exactly what you guys did, but let me just comment here, which is what you're seeing here on the screen, right, is a real pendulum, right? We built one, and right on the bottom of the pendulum, we put an Arduino to have essentially tell it's an accelerometer, which tells its location. So we were able to do a bunch of experiments, and this is with this guy, Taran Goran. He was an undergrad, and he built this. And you can see there on the top left, there's the little Arduino pulling in measurements of this pendulum, and there's the real data. And what was interesting about it, so what you're seeing there on the bottom left is the output of a Python notebook. So it got dx naught dt is 1 x1, and dx1 dt is some small amount of negative amount of x1, and then sine x0. Now, how do we get this? Now, it turns out the data was very important. It was critical that it went over the top. The only way you're going to get, so what we had is a bunch of trajectories where if you just had trajectories where the pendulum was swinging, it always would try to just build you a polynomial basis. That's what we found, at least for what we did. I think sounds like you found something similar. But what we did with this is we also swung it over the top. So it would maybe take a couple turns over the top, both to the left and to the right. And that's when the algorithm said, oh, the only way to actually satisfy this is if I replace all the polynomials with the sine, because the sine can go over the top. The polynomials can't. And so that's the only thing I can comment on, is that this will, it did work, gave us back the damped pendulum with the sine, provided we gave it the right type of data. And in fact, one of the tricks to making SINDy work really well is a diversity of diversity of data, a diversity of trajectories. That really helps SINDy find the right model.
Maybe the spurious terms due to the poorness of the data.
Yeah.
You're suggesting. Yeah, could be.
Yeah.
Okay, so let's do 5 minutes, because also Nathan has to take a coffee. Okay.
Yes.
So, okay, 5 minutes. 5 minutes.
5 minutes.
Okay.
I'm American. Are you hearing me?
I'm hearing you.
Oh, hi Nathan. No,
You're
I just
trying
want
to
to
reach America,
make
right?
a comment because
Hi, Adriano. You call me.
yeah, but just a comment related to what. Yeah. No, just a comment related to what you asked to Nathan. The thing that maybe something related to the orthogonality of the base you use it to write the dictionary, or because you said when you use monomials you got spurious modes, yeah. But when you use Legendre, so yeah, so maybe something related to the orthogonality of the.
My student who is working on this is here, Diego.
Yeah, I'm agreeing to you about these orthogonalities.
Can you comment? Can you provide us further details?
I don't have too much right now than plus than you talk about, but I think Hermite and Lagrangian is the best polynomial basis that we use, and because of the article for NodeCon, I don't work too much in these results, and I don't have too much to comment right now. But it is what you said, Professor. In the normal basis, we see that the dissipative term, right? And in the new basis, we don't. I don't have too much to comment right now, but I will see this in these days after finish the paper.
Adriano, are you working with SINDy?
I'm reading, not working yet, but I'm reading.
Yeah, we spent 1 year
Also,
studying. We started to do new things with this year. So the first year we spent learning the technique. In fact, I'm still learning. I think Diego understands better than me, but I'm still learning.
Yeah, but as Nathan told, I'm really interested in the biological part, the biological applications, the kind of regulation, path networks, those things.
In biology, there is a critical issue that is for instance, in an epidemic, your data, your dynamical system is multidimensional. You have some coordinates, some state coordinates, but in general, you have a measurement for just a few of these states or only a single state, or even not the state, there are quantity that is derived from the states. So you have the problem of hidden variables. This complicates a lot the use of the algorithm.
Nathan, I think if you're ready, you got your coffee, first of all?
I got my tea.
Oh, you have
Coffee. My other coffee machine's in the shop. It's getting fixed.
Ah, okay.
So I have to drink tea in the office and I go get my coffee, but I'll get that after we're done at 9.
Okay, great. Okay, so please go ahead.
Okay. Yeah, hey, so let's continue on. A couple finishing up comments about SINDy, for instance. Number one, we just recently put up PySINDy, which is a package that you can, download off GitHub. And what we've tried to put in there is a lot of our best parts of what we've done with SINDy, so that it works there in a robust way with some options. The second thing I will say is that for SINDy to work, oftentimes there is this idea that you need to have pretty clean data, and that's actually somewhat true. That we have been working on techniques to denoise, to sort of discover dynamics and pull out the noise at the same time. In fact, we're about to put another paper. I think we just put a paper up in the archive with this that kind of does a good job at trying to pull out noise. It makes it much more robust to discovering models. But it is, and then there's issues of also the fact that how do I think about this system when what I'm measuring isn't directly the state space. Everything I've shown you so far is I know what I'm supposed to be measuring. But let me give you an example related to the pendulum again. In the pendulum example that I just showed you, right, I actually attached a physical device measuring the coordinate. I knew the coordinate was theta and theta dot. What if I had just taken my phone and I had filmed it instead? Filmed the pendulum. In other words, my measurement space is pixel space. How would my pixel space know about things like theta and theta dot? I'm going to address that later. This is the idea of a latent space. In other words, what I measure is not necessarily what's on that inside. Okay. So that's going to be, I believe, let me just check here my flow. That's something we're going to talk about on Tuesday. First session of Tuesday. What I want to do is switch gears now and talk about everything I've been talking about is assuming that you already have the right measurement space. But really what I want to talk about is this idea of coordinates. You know, manifolds, embeddings, whatever you know, that's a fancy words for coordinates. So what can we do towards this end? So I want to move in a different direction a little bit and come back to this idea from Bernard Koopman from 1931. And, you know, there's a lot of talk nowadays about Koopman theory. And the reason there is because of this definition he gives here, and which is part of his original work, which is you take a nonlinear dynamical system, dx dt, finite dimensional, and there exists a measurement vector, g of x, which actually is a functional, okay? So g of x moves you to an infinite dimensional space where the Koopman operator k acting on g of x just gives you back g of n of x. In other words, it takes this nonlinear dynamical system of finite dimensions and makes it linear in infinite dimensions. This is an amazing concept because what we know is nonlinearity is very difficult to deal with often. And this is telling you, if I just have the right set of observables, I can turn my problem linear. And the great thing about linear problems is you can write down the solutions. This is what we teach all of our students, is how to solve linear problems. And we tell them, like, once you know how to do this, you can do lots of things. And then later they find they're disappointed with us, I think, because the world's all nonlinear. So, or all the interesting problems are nonlinear. So we need to figure out how to solve those. All right, so how do we do this? Well, the first algorithm that really came out towards computing this Koopman operator, in other words, this representation, was called dynamic mode decomposition. It was developed by Peter Schmidt, in which he was doing it for fluid dynamics, in which he took snapshots of fluids, and then he said, okay, so how do we do this? And he came up with this dynamic mode decomposition algorithm. What it is, and we've kind of worked on it a little bit, quite a bit too, which is to try to write it in a simpler form, is you give me a set of snapshots of the dynamics. Let's call that x. x1, x2, all the way to x of m. So I have these snapshots. And x prime are all those snapshots advanced delta t into the future. Now what Koopman's looking for is a linear model, a regression to a linear model. And what DMD does exactly that. It says, oh, well, so if I go from x to x prime in the future, find me a matrix A that is the best fit, least square fit matrix that takes all those snapshots and it best fits all those trajectories from x to x prime. And what you can do is you can find it's given right there at the bottom, a of x is equal to x prime times the pseudo inverse of x. And this now gives you then a linear dynamical systems model for how the data is evolving. It's the best fit model for all those trajectories you have there. There is a more sophisticated way to do it, and this is work with Travis Askham, who is a former postdoc, in which you say, oh, well, linear solutions are just exponentials, and that's exactly how Travis formalized this, so to make a better model. So what's the power of a dynamical system that's linear? Well, the great thing about linear dynamics is that they're easy to solve. So if I have a linear dynamics dx t equals a of x, then I can find its eigenfunctions and eigenvalues, and I can write down any solution in terms of an eigenfunction expansion. And with the idea that this new variable x tilde, which I'm working in, is somehow approximates the full nonlinear dynamical system. So this is just another regression technique which says, find me a way to approximate this nonlinear dynamics with the best linear model possible. Okay? So where can you start using these things? Well, we used it in quite a variety of applications. So, so for instance, you know, we did financial trading models, right? So you can start saying like the financial markets are, its time series data is quite stochastic looking. But what you can do is say, well, I can build this linear model from snapshots. So I get a best linear dynamical systems model on the fly as I move along. And so you can use this to sort of do short time future state predictions and do trading. The other thing you can do is something like computer vision applications with this. On the left there, what you see is a way that we did background removal. In other words, you take time series of basically video, and what does the zero eigenvalue correspond to? E to the 0t is something that's not changing. So what you do is you take this video, you do the eigen decomposition, and you say, okay, the zero eigenvalue is the background, everything else is foreground. And what you're seeing there is what we are able to do with this. Essentially, the middle panel is all of the eigenvalues that aren't zero, and the right panel is the zero eigenvalue, which is essentially the background with no cars or people. Isn't that kind of interesting? Kind of fun. So you're treating video as a dynamical system. We also did this with ECOG recordings. So this is getting closer to biology, where we took this local model essentially of DMD in a window, and we're able to sort of basically start to understand some of the characteristic nature of spatial temporal data in the frequency content for what are called sleep spindles. These sleep spindles were these little bursts of activity in different parts of the ECOG recordings that you could pick up. And we were able to see that there was these different clusters of spindle networks for sleep networks. Importantly, once you have a linear model, you have something quite amazing in addition, which is you have the ability to start learning data-driven control models on the fly. So what you're seeing there is control systems. I always think of control as being x dot equals ax plus bu. That's how you're going to be able to get good control. Now remember that this DMD is a regression to x dot equals ax, a linear model. You can basically reshape DMD to include controllers and regress to x dot equals ax plus bu. So now you have this generalization of this model regression, which allows you to account for actuation of the system. So that way you can disambiguate what is a kick to the system, creating dynamics versus what is the actual underlying dynamics. Okay, so that's a really nice part of an innovation around this DMD architecture. You can also start thinking about this from the point of view of pulling apart multi-scale physics. So there's this aspect of taking windows of building DMD models and saying, let me look at DMD model in this window, and smaller windows, smaller and smaller. So smaller windows, you pick up fast physics. Big windows, you pick up slow physics. So this is very much what you would do in something like a wavelet decomposition or an analysis of signals where you have different spatial temporal dynamics happening at once. And what you can do with this is you can set up this DMD architecture very easily to handle slow scale physics to fast scale physics. And you can decompose them in such a way that you get all the kind of right dynamics versus just looking at all the data at once. Now, the reason this is so important is I'm going to give you an example of this. And my hope is this makes a lot of sense because I think this can have a big role to play in something like biology. And here it is. So what we did is took sea surface temperature data. And we took this over a 20-year period, 1990 to 2010. Now, if you do analysis of this data, just as it is, you'll see that there's these large scale structures, like so panel A up there, that's kind of like what you expect. This is like your average temperature profile, and that's like the most dominant feature of the data set. And then you start looking at at other features like doing a PCA analysis, you get other features, but there's a few things you miss completely, like the El Nino phenomena. El Nino is a intermittent phenomena that shows up only once in a while. So if you look at the overall data set over 20 years, it leaves a very small signature. But if you now do this multi-resolution idea where you look at a 20-year period, 10-year period, 5-year period, 1-year window, you start seeing what's important in these different windows and decomposing it this way. What you find then at the level 4 decomposition is panel C there, which is you find El Nino just pops out. So if you're doing data-driven modeling and you didn't know El Nino existed, this would tell you there is this giant mode that comes on in 1997. Maybe you should take a look at it. This mode is completely buried in a PCA type analysis. So this is a really nice feature of something like this multi-resolution architecture, because it allows you to get after things that are intermittent phenomena and transients. And in biological systems, if you just look at some of these whole brain recordings that people are doing nowadays, there's a lot of intermittent and transient phenomena. And if you just PCA everything, you really wash it out. But this is allowing you to get after key structures on key windows of time. So how can we improve this DMD architecture? Because DMD is just simply take the data, build a linear model. So one of the things that we can start thinking about is saying, okay, well, I want to do this Koopman idea. Koopman said there's a function of the observables that allows me to make things linear. So in other words, let me talk about it this way. What you're seeing in the middle right is some complex system that you're measuring. So you take measurements and you construct these data matrices X and X prime. In other words, snapshots and how they advance delta T into the future. Okay, so that's your data. What I just showed you with DMD is if you take the bottom pathway there, is you take those observables, you do this regression, and now you have a linear model directly on the data of observables. What Koopman says instead, well, what if I were to not work with X and X prime, but some function of X and some function of X prime, so some G. I'll have to prescribe what it is, but now I move to new data matrices Y and Y prime, which are these G of X's. The whole goal here is to pick a G of X such that this model is more linear. In other words, now you do DMD on those variables with the goal of picking good G of X's that gives you a true linear model. I'm going to give you an example of this right now. In other words, you don't work with the original coordinate system. You work with a new coordinate system that you prescribe so that to make it linear. So let me give you an example. Here is a simple top left 2x2 differential equation. It's right out of the back of any of these differential equations books when you're doing phase planes, right? Like here's your 2x2 phase planes that you would sketch. It's nonlinear because it's got the x1 squared. And so you could, sketch out a phase plane. There's a fixed point at the origin, and then you sketch a phase plane. And that's actually the bottom surface of this 3D plot here. But notice the following. What if I make a coordinate transformation? So on the top right, I've defined y1 is equal to x1, y2 is equal to x2, and a new variable y3 is equal to x1 squared. In these new coordinates, that system is exactly linear. This is exactly what a Koopman embedding is. You're going to take you move to a new coordinate system in which the dynamics, which was originally nonlinear, is now linear. Okay, so this is a closed form solution of showing it. By the way, getting this thing to close is very difficult, and there's conditions on in which this works, but this is a concept of what you were trying to do with Koopman. Okay, let me show you another example. This is the Burger's equation. So if you do PDEs, this is one of the first PDEs you learn that has nonlinearity in it. And it's hard to solve because it's generating shocks. And you learn about like solutions that create shocks, and then you have to have figure out what happens when a shock forms. And so there it is. It's basically an advection, nonlinear advection with some, but now the way we do this is you put a diffusive regularization. So Burger's equation is this famous equation from out of pre-1950s, really trying to understand shock waves and fluid dynamics, right? They were looking at aerospace applications. Cole and Hoff in 1950 and 51 sort of simultaneously discovered that transformation there, that if you look at it there in the middle of the page on the left, there's a transformation. It's called a Cole-Hoff transformation. Remarkably, that transformation takes that nonlinear PDE and makes it linear, turns it into a linear heat equation. So this is kind of a remarkable thing. You started off with a nonlinear PDE, and now in this new coordinate, you've made it linear. This is exactly what a Koopman transform is trying to do. This is and now in this space, what's great about being in this space is I know the solution to the heat equation. I can write it down on pen and paper. Not only that, it is more parsimonious representation of the dynamics than the original Burger's equation. So you have a lot of advantages by moving into a new coordinate system and doing your analysis in that coordinate system. Okay, so let me give you an example. And I don't know how familiar you guys are with these different examples I'm giving. I'm just putting them out there, and hopefully they work. And who cares what they are? It's more to just represent a point, which is you can take models, and by enriching your parameter space, you can, or your observation space, you can use these DMD models and make things more linear. In other words, if you notice what I did in the first part of this talk, I talked about take your measurements, build a nonlinear model. This is going in a completely different direction. Take your measurements, make a transformation so you don't have to have a nonlinear model. You get a linear model. Okay, they're two different things. Later on Tuesday, we'll try to tie these two together, use both of them in conjunction with each other. But for right now, this is really going at this in a very different philosophical way. So here is this, what's called the nonlinear Schrodinger equation. It's some nonlinear PDE. Who cares? It generates some dynamics that you see there on the top left. It's a breather state. This is just this little lump that breathes. So the question is, and it's really generated by nonlinearity. So if I were to do a linear approximation to that, if I took that state and say, let's do this dynamic mode decomposition and just do a least square regression to the best fit linear model, I'd get the B there that you see. Okay. Question is, can I improve this? And by enriching my set of observables, so what we're going to do now is take this Koopman approach. So on the bottom left, you see I picked observables now being x and mod x squared x. And the reason I put mod x squared x is because that's actually the form of the nonlinearity I have in the equation. So that's inspired that. On the bottom right, I picked x and mod x squared. It's quadratic, but it's an observable. And so I just say, how well do these work if I now do a linear model in those coordinates? And you can see on the bottom right, I did not do very well. In fact, I did a lot worse. But the bottom left looks very much like the top left, which it's supposed to look like. And in fact, if you pick the right observables, you almost get a solution that's accurate to the numerical precision I ran those simulations in. So that's the middle panel. All the eigenvalues are supposed to be on the imaginary axis, and they actually are. That's how good the approximation is, simply by not working with x directly, but by working with some function of x. So the point of this problem partly is in part that if you get yourself in the right coordinate system, great things can happen for you. if you can really find a coordinate system that linearizes the dynamics, it's amazing, right? Because now you have a linear model. You know everything about linear models, right? Once you have that, you can set control up in there. You have eigenfunctions, eigenvalues. It tells you everything that's going to happen in that model. You can write down pen and paper solutions. So part of what this whole Koopman push is this idea of, can I find myself a better coordinate system where my dynamics is being made more linear or exactly linear? And some of these I've shown you exactly linear, and some of these I've just made it more linear so that the DMD approximation actually works amazingly well. Questions on this so far? Okay, I can come back to this. I'm going to skip up here in my slides and really start to hit some important issues here that still remain. Okay, so let me highlight, you know, I'm giving you this talk as if, hey, look at all this stuff you can apply, and I've shown you how it works on these examples, but there's still a lot of problems, right? So I don't want to mislead anybody to think like, oh, once you have these methods, everything's going to work for you. No. It means that you have new tools and you have ways to handle things, but there's a lot of really challenging issues still on the table for you to think about. Some of the challenges are just around how much data and measurement you have. One of my biggest frustrations in working in the biological sciences is that oftentimes you're just really constrained by how much data you can collect reasonably, right? So for instance, suppose you work on an infectious disease. How much are you really measuring of the system, right? You're trying to measure sick people. Like, you know, everybody's building these COVID models now, right? And but it's hard to get an accurate assessment of how many people have it. A ton of people don't test. There's whole regions that don't really have much data, right? How do you build models with really limited measurements and data, right? I mean, this is really challenging. And I find it especially challenging in the biological sciences. In a lot of physics systems, you can kind of set up an experiment that allows you a lot of access to your measurement space to do more precise measurements. But biology is sometimes just really difficult to do that. You have noise in your system, though it's always challenging to deal with. You have multi-scale physics. One thing that really I think is the grand challenge for us is in our generation right now, maybe I don't know, I'm counting myself as a younger generation, even though I'm probably older generation, but we're really good at, you know, solving, I call it uniscale physics problems. I write down some governing equations, you say some things, but if you look at the grand challenge problems we're trying to solve now, especially in biology, they're all multi-scale physics. These are different models at different levels that are connected together. Micro scale connected to meso to macro. They're all coupled. They're all different models at each level. Really hard problems. How do you handle that? Another issue brought up, latent variables. You measured some stuff, some quantities of interest. How do you know there's not a bunch of, how do you find all these other variables that are affecting it that you didn't measure, that maybe you don't even know exist? So first of all, you just have to know they exist. Second, once you have it, how do you model it? Latent variables are a huge issue in a lot of physics systems or biophysics systems. Parametric dependencies, a lot of these models depend on parameters that change, like, hey, it heated up today, so the dynamics is slightly different than yesterday when it was cold. How does a model handle that when it's trying to put one parameter in instead of accounting for some parametric dependencies? And then stochastic systems. So what I want to spend a little bit of time I have left is for today is just talking about how we've gotten around some of these challenges of things, because some of these things are really important to handle in real systems, right? So part of the questions that are being asked is, I tried SINDy on this or that, and especially as you go to real systems, then you're going to have some of these problems. Really, they're not you know, abstractions. They're reality for you to have to deal with. So I'm going to cover a couple of these and how we started to handle them, and then we'll end for today.
May I
So
put a question on the
yeah.
previous slide? Yeah, and what about another, maybe to challenge this, when you have like a time series data set that the data are correlated with unknown delayed times. Now, for example, X1 is correlated with X2, but with different times, and you have delayed between these variables. How you deal with that, with this?
Oh, yeah.
They
So
are correlated, non-linearly correlated, not the linear one, non-linearly correlated on delay times.
No,
Professor,
yeah, go ahead.
So can you comment about higher order DMD, because it's related to Ajmer questions? Maybe it's related in the terms of the memory of the problem and the correlation between variables in time.
Yeah, yes, they are correlated. Yeah.
Yeah. So this is interesting you ask about time delays, because one of the things that we've been really pushing on a lot lately is time delay embedding all your data, right? So there's a couple of things that happen with time delay embeddings. One, if I measure, for instance, a system that has 3 degrees of freedom, let's go to the Lorentz system, which is x dot, y dot, z dot. I have some time series, but I only give you measurements of x. I don't even tell you there's a y and z. Is there any way you could know there is a y and z? So what we've done is we've said, okay, take the x data and build what's called the Hankel matrix. So now you do is you take that time series and you time delay embed versions of that time series on top of each other in a matrix, the Hankel matrix. Now, if you do a singular value decomposition on that matrix, what you find is the dominant features of that have 3 modes that matter. In other words, it's telling you there's a y and a z. It has a signature of it there. In fact, what you see is the shadow of the attractor, which is the Lorentz attractor, in this embedded coordinate space. So there's a lot that's being done these days with time delay embeddings. And in fact, the generic way I always like to tell people to do DMD, so if you've already know DMD, and then I showed you some of this, you go like, okay, that's just standard DMD. If you haven't seen it, so you learn something. But if the way I use DMD now is to take time series data for the system, time delay embed it, then do a DMD on it. That's a much more robust way to do it. It handles latent variables. It handles this dependency on delayed times. It does a lot of things for you and helps you build a better linear model.
Nathan, regarding your comment using Hankel matrix, you're talking about Havok, correct? Especially in epidemics, I'm thinking in particular in COVID data sets. You have a tremendous underreporting and a tremendous delay, which sometimes by a random factor, the notifications of some days accumulate and are reported in a single day. So you have some enormous jumps, and the data is completely crazy. It's a I like to say it's a completely distorted picture of the reality. How this can make the things difficult in this idea of using delayed coordinates to try to recover the latent variables. I think I tested Ravok. I know it works well when you have reasonable data, but the real data, it's a mess for real epidemics.
Yeah, I mean, that's a good question. I mean, so I always think there's 2 flavors of, maybe 3 flavors of real data. There's the real data where, yes, there's some measurement noise, but it's not too bad. You know, like you can somehow engineer a system to keep the noise down. And so you get actually a pretty clean representation of the system. Then there's data that's pretty noisy, but you know, it's noisy in sort of a dependable way. It's not like this week it's noisy this way and this week it's noisy the other way. Because I think what you're talking about is the 3rd class of data, which is it's all over the place, right? You're finding that like these data measurements can are not only corrupt, underreported, and maybe with big delays, but also it could change week by week how exactly it's gone wrong.
Day by day.
Day by day. And so let's be honest, it's really hard to build models in that environment under any circumstance.
Totally agree.
And I don't know how you get a truth out of that even. Because it's almost like you need a model for how the corruption is happening.
Mm-hmm.
Like if you could have a model where say like, okay, here's my model for how the under or over reporting is happening. Here's my model for how what they did for this, that. So that you could maybe in some sense bring that data back into some reasonable way. But the fact of the matter is that that typically doesn't happen.
Mm-hmm.
So I guess I don't really have any good comments for that. That's just really hard data to work with. I mean,
this data is not, it's not close to reality. It's absolutely far from the reality, but it's the only piece of signature that you have from the reality.
Yeah.
It's really difficult to work in this situation.
Yeah, no, that was just really difficult. Unless you had some kind of underlying model you trusted that you could do an assimilation to. Like, for instance, suppose you believe that SIR is still a basic good model for that. You could then use this data and assimilate it with that SIR, even if it's even if you don't trust that data, you could put some error bars on it. But a simulation is one way to do this, potentially, right? Because you're right, it's your only peek into what the truth might be. It's at least a data point that somehow, even if it has flaws, it's some reflection of some reality that's there. But very difficult.
I usually joke that this data is a picture of a reality. You point the camera to the left corner down, and you add noise, and this is the picture of reality you have. A piece of the corner extremely corrupted with noise.
Yeah, that's probably right.
Totally non-informative.
Yeah. All right. Well, let me continue here, and then we'll get into some more discussion. So first, how do you handle multi-scale systems? That's a challenge. I already showed you with DMD, you can do this multi-resolution analysis, but you can do something similar here also with SINDy. In fact, let me just show you this picture. What is this? It would be really hard to say what kind of dynamics this was, right? If I just showed you, here's some time series, it's so short. You might say like, it'd be pretty hard to discover dynamics from here. But in fact, Kathleen, here she is, she just graduated this last year. She did this. So Kathleen was looking at this and she amazed us. She showed us this in the office one day. And we were amazed that she could do this. You see the blue trajectory on the Lorentz system? Up until Kathleen showed us this, we thought if you're going to discover the Lorentz system, you probably have to see it switch lobes a couple times, circle around here, jump over here. You know what we normally see is something like this butterfly attractor. She could discover it just from that blue trajectory. In other words, you don't even know there's a second lobe. It's just a short burst, but very well resolved and very clean derivatives. You can discover the model. Now that led us to start thinking about sampling strategies for multi-scale physics. In other words, if I want to discover the fast scale physics, sample on a fast clock. And if I want to discover the slow scale physics, sample on a slow clock. In other words, disambiguate these. And then also if they're coupled together, you can discover that coupling. That's exactly what she did here. What you're seeing there is a fast scale and a slow scale physics systems. They're coupled together linearly. And she not only can identify each individually, but then can also discover how they're coupled together. So you can really discover multi-scale physics. And in fact, we found some really nice sampling strategies for this so that you can do burst sampling, so that you can do in bursts, very fine sampling in time to get the fast scale physics, and then do these bursts on the slow scale to get the slow scale physics. And this is a paradigm that works well for this model discovery structure. We also follow this up with discovering latent variables. So again, this goes right back to what we were talking about, which is time delay embedding, which is you can do time delay embeddings, and time delay embeddings really help you see the shadow of the structure that was there. So even if you don't have the actual, you don't even know there was a Y and Z, for instance, what I said here, just have X alone, you discover that actually there is a Y and Z. I don't have direct access to it, but I can build a shadow model for that and understand that there's a higher dimensional subspace I have to work with these latent variables. And we can do this also within a SINDy architecture, discover latent variables. And then one last thing I'll just finish here is, what about parametric systems? What if I have some dependencies in the data? So for instance here, this is again with Sam Rudy, what if in going back to Berger's equations, what if the advection was time dependent? In other words, the parameter that's changing in time. So if you do just generic SINDy, it's trying to pin that to a constant and it can't, so it uses a lot more library terms. It doesn't discover the right governing equations. In other words, you have to disambiguate the dynamics from the parametric time dependencies. And what he came up with is a method by using group sparse thresholding, and you can do this. And so now what he's able to do is discover the difference between governing equations and parameters of those governing equations that are changing in time, which again, I think is very biologically relevant. And so for instance, here, he can get some of these models out. So for instance, if your fluid flow, if the Reynolds number changed, this is where a lot of these model discovery techniques would break down. But this says, oh, it's the same model. It's just this parameter changed and it handles it no problem. And so that's a kind of a nice thing that this is able to do. I think I'm going to end there and take questions. So.
Great talk, great lecture, Nathan. Thank you so much.
Thank you.
Already, some of my students already are thinking to work with you.
All right.
Okay, so let's see if someone else has more questions. Yeah, I have more questions about the epidemics, but maybe I will ask you privately. Let's see if in the YouTube.
Any questions? Yeah, feel free.
Yeah, no, just say excellent lecture. Just
I'd like
yeah,
to
no,
ask a question from the beginning. I lost this in the first slide, Nathan. May I ask you?
Americo, please, just a minute before going there, about this time delay in bidding, if Kurt could talk a little bit more about this Hankel decomposition, but if you have non-linearities on this delay in bidding things, can you do this decomposition when you have these non-linearities in these time delays?
Yeah, okay, that's a fascinating question. So let me answer it this following way. There is a theorem by a group from Italy, Bozo et al. And this just came out, I think, not too long ago. And they were looking at time delay for geophysical systems. They're trying to predict volcano activity or something like this. And one of the theorems they proved was, if I delay this in a fully nonlinear system, and if I delay this sufficiently amount of time, in other words, in the infinite delay embedding limit, that Hankel matrix will move me to a coordinate system where everything is a Fourier transform. And in fact, you can really easily do this. You can take something like the Van der Pol oscillator, which is just a 2x2 nonlinear oscillator, which has these interesting nonlinear oscillations, and you start time delay embedding it. And if you've done time delay embedding this enough, it turns into exactly Fourier modes. So it's really interesting. So I think there's still a lot to learn about time delay embeddings. And we've been playing around with it and we can't quite, I understand more than I did, but I don't quite understand all of the power of time delay embedding. It's a fascinating subject and there's still so much to be pulled out there.
Yeah, I agree with you. Okay. Sorry, Americo, for jumping.
No problem, Jamiro. You're always asking great questions. Nathan, could you show the first slide you presented? Not in this part, in the first part.
Oh, the DMD?
No, not the DMD, the general framework in the beginning of the course.
Yeah. So like, I think, right.
Where you show coordinates and governing equations.
This one? Oh,
no.
Oh, you want, okay, I see. You want this one. Yes.
No. Yeah, this one. Yeah.
Okay.
So you mentioned it's choose the right coordinates is critical because if you choose not the wrong coordinate system, let's call it this way, it made your equations more complicated. Choosing the right coordinate system is critical to simplify your formulation. But your data, maybe if you have limited data, you don't have enough information to discover the simplest coordinate system that parameterize your model. So your system. How critical is this? Suppose because even with not a simple coordinate system, you may formulate a consistent model for the system of interest. But of course, if you could choose the best one, if you have some kind of curvature, cylindrical coordinates work better than Cartesian, but you can formulate your problem in Cartesian coordinates. What are the fundamental ingredients to find the good coordinate systems? This is my question.
Yeah, this is a good question. I'm going to go back to this one because part of the reason the Ptolemaic system was around so long is they came up with a model and it worked really well. That circles on circles model was amazing. That's why it was 1500 years because, you know, despite the fact that even when Kepler and Galileo first came out and said, actually, these are elliptic orbits and here's in its heliocentric universe, it still took close to 100 years before, actually, how long did it take? So really for widespread adoption, people were still using the Ptolemaic system because it was so accurate. And in fact, when Kepler first came out, his predictions weren't as accurate as the Ptolemaic system. So is the Ptolemaic system a wrong model? It's just a model. Who can, I mean, it works, right? I mean, this is one of the big questions we have to think about in modeling is like, you know, that Ptolemaic system, yes, it was wrong, but it could use worse data. And in fact, it took Tycho Brahe's data before we could really get that Keplerian system in place. And it really took a while for it to be adopted and actually beat the predictions of what we would say is a lesser model, which is the Ptolemaic system. My own personal opinion is when you come to something like this, you do what works. And that's why I always like to go back to this is like, well, what's the quality and quantity of your data, right? Back with me. Okay. What's the quality and quantity of your data? Because you actually make decisions based upon the answers to this question, not what you would like. I mean, here's what we would all like. I have great data. I have so much data. And I have all the possibilities to be, I've observed everything. Well, you know, model building is pretty easy there. More likely is where in the situation is it's crappy data, so the quality is low. I don't even have very much. I'm not even sure what I'm observing. I took this sensor and I put it in there and I got some recordings. I don't know. So it's observing some of the dynamics somehow, right? It's some representation of what I'm observing. And what I always do is think about answering some of these questions. One of the reasons I like dynamic mode decomposition so much is I can always get a model out. Because I can do that linear regression, come up with a linear model in any case. That's your low-end model with little data, maybe even bad quality. If I get much better and cleaner data, maybe I could do SINDy. Maybe I can even do SINDy and discover coordinates. And that's what we're going to talk about Tuesday.
Mm-hmm.
So I know that's not a very good answer, except for that if you're a domain scientist, you're much better poised to answer those questions, which will dictate what you can use versus you deciding to use something and the data just isn't up for it.
Mhm.
Okay, so yes, I think Nathan would be good to have some references, so maybe people can read between here and Tuesday, and it would be great. So, or even some more exercise people can kind of test.
Sure. In
without
fact,
going too complicated, just to see in the short time things might work. So I bet I know you teach. Are you still giving a course on the Coursera? Are you still? Do you still have?
I don't, but I have a bunch of open source. I have a bunch of stuff up on YouTube. So tell you what, I'll send an email to you, Stefanella,
Yeah,
later
please.
today with
Yes.
a couple extra lectures where I actually code some stuff up, have code
Great.
there, people can play with it, as well as
Great.
to some of the books that we do.
Yeah, because we already have some eager students that would like to get their hands. Very much. Thank you. Wonderful lecture.
Okay, so I'll see you guys Tuesday.
Yes, the same time. Thank you
Okay.
so much. Bye-bye.
Bye. Bye, guys.
Bye-bye.
Bye-bye.
Bye. Thanks, Nathan.
Bye.